kids. So let's just go over a few things. So I believe where we left off is Lewis structures, and Lewis structures we went over recently, and we'll go over more in a couple days. But oops, that's not what I wanted. Here we go. All right. So Lewis structures, to get the Lewis structure, you need the symbol of the element, and then you need dots to represent all the valence electrons. So 1 dot per electron, 2 electrons per side going all around. And that's basically because there are 8 valence electrons possible, and we want to represent it on each side, the north, south, east, and west, basically. So here are examples of pretty much everything you'd ever have to do with a valence electron. And recall that we're talking about the outermost electron. So all of group 1 has group 1 valence electron. All of group 2 has 2 valence electrons. The transition metals will have vary from 1 or 2, but won't go into 3. Recall that, like, when we're filling up this row, it's everything argon is plus you're down 1, 2, 3, row 4. So you're in the 4th energy level, the 4th shell away from the nucleus, 4s block 2, and then we drop to the 3d. So this is 3d. That's why they don't count toward the valence electrons. And then we go back in the p block to the row we're in. So this is 4p. So the only electrons that count toward valence are the s and the p, because the d, when you fill those in, you've already started the s from the more outermost electron shell. So that's 3d, 4p. This is 5s, 4d, 5p, etc. So, and notice here they do the north, south, west, and east side of the atom. You put the symbol of the atom in the middle, and the dots represent electrons in the valence. So we're not going to exceed 8. You can see here the valence of the noble gases is always 8, the exception being helium, which only needs 2 because it's only got an s to fill. And we're only talking about outer s and p electrons. All right, so here's a Lewis dot diagram for oxygen. Oxygen has 6, either because it's in group 16, and group 16 all have 6. The 10 minus from 16 is 6. So there are 6 valence electrons. It's also because of the electron configuration. So let's take a look at silicon. Silicon here, it's number 14 on your periodic table. And if we were to do the electron configuration for silicon, I guess we could take a look, even though this is going to ruin it. So silicon is here. There it is. Silicon is here. So it's everything that neon is plus 1, 2, 3, 3s2, and then 3p2. So silicon is everything neon is. 1s2, 2s2, 2p6, 3s2, 3p2. So it's everything neon is. 3s2, 3p2. And that's important because we have inner electrons being put in here. These are the outer shell electrons. 3 is the highest shell number or quantum number here, principal quantum number, and we're putting in 2 electrons in the s on the 3rd shell and 2 electrons in the 3p subshell. So it's a total of 4. So our valence electrons, long story short, is 4. And if we were going to draw Lewis dot, which I guess I will attempt, I'm going to attempt, and I guess we'll keep. So you would use the symbol SI, and now we need to put 4 electrons around here. So you'd put a dot, and you can put them on 1 on every side is fine. 2, 3, and 4. So that's what the Lewis dot configuration for silicon would look like. Let's do another one. So if we're going to do bromine, bromine's atomic number that's the number of protons, that's 35. And the electron configuration, if you pull out a periodic table, bromine being 35 is going to have everything that the noble gas closest to 35 without going over is argon, which is 18. So it's everything argon is. And then we're in row 4, so it's 4s2. We're going to do all the 3d. 3d does not count as valence electrons because it goes down a energy level. It's a lower shell than the outermost shell. And then we're going to go back into the outermost shell, the 4 shell, and we're going to put 5 in the P there. So the total number of electrons in the outermost shell is 7, and you can also figure that out because bromine is in group 17, the halogens, and 17 minus the 10 is 7. And so the Lewis dot for bromine would look like it's the symbol of the element, which is a Br. And then I'm going to need to draw 7 electrons around this Br as dots. So there's 2 up here and 2 over here and 2 down here. And that's a total of 6. So I need one more is 7. And you could have put that one on any of the sides. I wouldn't be unhappy. So that's how we do electron dot. Now this brings up the diatomics. Now the diatomic molecules, if you think about, the easiest one to do is hydrogen. So hydrogen's here, and hydrogen has 1 valence electron. It's in group 1, so it has 1 valence electron. And then here comes another hydrogen. So when hydrogen is created, it's never created with just 1. There's always going to be a second one or multiple nearby. And because of this, hydrogen needs, it's in a unique situation where it needs just 1 more electron to be like a noble gas, to be like helium. So hydrogen here, when it's created with another hydrogen right next to it, it's like, hey, I need 1 more electron to become a noble gas. You need 1 more electron to become a noble gas. Let's make it happen. And they'll turn those electrons into a bond upon, they'll start sharing these 2 electrons, and you'll form H2, and you'll have H2. And that's called a diatomic because pretty much you can't go out and find just 1 hydrogen atom. It's always going to be paired with another one, and this is due to its unique property that they're just 1 electron away. This is also going to be true with all the halogens. So fluorine, chlorine, bromine, iodine are all 1 electron away. So if we look at, let's look at chlorine, just so I'm doing something different than what we just did with bromine. So there's I shouldn't have done this because C's are much harder to draw than B's, but that's all right. It's a little shaky, but you get it. All right, so this chlorine has 7 valence electrons, as does the other one. So here's 7-ish, 7 valence electrons. And here is 7 valence electrons for this one, the more quivery one. And the point of all this is they are each 1 electron away from having the noble gas configuration. In this case, chlorine is trying to be like argon. So since they're sort of created at the same time and there's multiple around, there we go, we can then make a bond with the 2 that are unshared, pair those up, and you'll get Cl2. And that will be true for any of the halogens. Now, oxygen and nitrogen are the only sort of non-obvious choices here. Hydrogen just being 1 away, all the halogens being 1 away, that makes sense. Oxygen and nitrogen, though, have very high electronegativities. So when they're created, they're just really geeked up to make something happen. And as you can see here, hydrogen or oxygen would need a double bond because oxygen has 6 valence electrons. So it's going to need to share 2 with another oxygen to have a total of 8. So 1, 2, 3, 4. And then there's 2 more in here. 1, 2 that it's sharing. And then this other oxygen has also got 2 that it's sharing. And then the other 4. So that's a total of 6 for each oxygen. And that's why it double bonds. Nitrogen has a total of 5 valence electrons. So it's going to have 3 looking to share. I guess I'll do that just because I'm here. So let's do that with nitrogen. Nitrogen will have 5 electrons and it'll want to share. So that's 1, 2, 3. I'm drawing it this way just because I know they're going to want to share them. And then this nitrogen has 5. 1, 2, 3. And so to be a diatomic like that, it's going to have a triple bond. So 1, 2, and then 3. And it should make sense to you that a single bond, like here and here, requires a certain amount of energy to break that apart. And that is not as much as breaking apart a double bond. If you think about, 1 bungee cord or 1 chain holding these together. This is now 2 chains. This is now 3 chains. So the more bonds you have, the harder it is to break apart what you got. So nitrogen would require you break 3 bonds to break them apart. Oxygen 2, hydrogen, chlorine, only the 1. All right. So the way to remember this, there's 2 ways to remember this. One is that they make the number 7. You'll see here, this is kind of like a number, 7. Let me just write it over there. Look, that looks like a 7 almost. But there's 1, 2, 3, 4, 5, 6 that make that number 7. And since it's trying to tell you there are 7 of these, you remember hydrogen as being the most obvious one. That is included in that 7. The other thing Quigley likes is Brinkelhoff, which tells you bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Brinkelhoff, if you remember that word, you'll remember the 7 elements that require diatomic rules, basically, that they'll form diatomics almost immediately in their natural state. All right. Then we got into molecular geometry, which is why we did all this. And these rules are a little onerous, but they really do help you as you're learning this as just sort of rules to follow. And the point of the matter is, since we only use valence electrons for bonding, you're going to add the valence electrons for all the atoms involved. You're going to adjust the charge if necessary. So if something has a positive charge or a negative charge, you're going to need to add or subtract electrons for that. Remember, electrons are negative. So if there's a negative charge, you're going to add electrons. And because they're negative, you're going to need to remove electrons if there's a positive charge. So we'll see this in action in a minute. Determine the central atom. The central atom is always the first one listed unless you have a hydrogen first. Remember, hydrogen listed first indicates that you're talking about an acid. So HCl is an acid. H wouldn't make for a very good central atom because it can only make 1 bond. So we always use the next atom over if it's a hydrogen. Otherwise, we just use the first one listed. Connect all the other atoms to the central atom with a single bond and subtract 2 electrons for every bond you just made. So it takes 2 electrons to make a bond. So if you've made a bond, you need to subtract 2 electrons from the total amount available to you. Complete the octets for the terminal or external atoms first. Remember, hydrogen only needs 2 electrons. So just once you bonded a hydrogen, it's good to go. You don't need to add any electrons to it. Place leftover electrons on the central atom, and then if necessary, you use a double bond. So here's water. Water is made up of oxygen, right? Hydrogen and oxygen. So the first step is add the valence electrons. So oxygen, there's 1 oxygen, has 6. Hydrogen has 1 valence electron. There are 2 of them, so it's a total of 8 valence electrons. Step 2 is adjust the charge if necessary. There's no charge on water, so there's no +1 or +2 up here. So we don't have to worry about adding or subtracting electrons for that. Determine the central atom. It is not going to be H because even though it is the first one listed, that's a boring one. So we're going to start with our oxygen in the middle. And then we are going to connect all other atoms to the central atom with single bonds. So the central atom is oxygen. We're going to single bond 2 hydrogens off of that. Each of these bonds has 2 electrons in it, if you recall. So there's 2 electrons there and 2 electrons there. So our total was 8, and we're going to subtract the 2 for this bond and the 2 for that bond. So -4 for a total of 4 electrons left in this picture that we're trying to draw. Then the next thing says complete the octet for terminal or external atoms. So these are the terminal atoms. They're not the central atom, the hydrogens. They don't need an octet. They only needed the 2 electrons to be whole. So we're good to go with that. Oops, jumping ahead. Place any leftover electrons on the central atom. So the central atom is oxygen. We have 4 leftover electrons after we've done all our bonding and completed our octets for the terminals. So we're going to add 4 electrons here to the central atom. 4 minus 4 means we have no electrons left. And that is what the sort of shape of water, to quote a recent movie, looks like. All right. I can't take questions, so I'm going to move on. So phosphate PO4 minus 3. So now we do have a charge to worry about. Phosphorus is the central atom. It's the first one listed. It has 5 valence electrons. There's only 1. Oxygen, there are 4 oxygens. Each oxygen comes with 6 valence electrons times the 4 is a total of 24. You're going to take a charge of a -3. So since it's a -3 charge, we're going to need to add 3 more electrons. Remember, electrons have a negative charge. So if we have 3 more electrons than protons, we're going to need to add 3 electrons to account for that. Our total when we add up 24 plus 5 plus 3 is 32 valence electrons. First thing we do, we take our central atom and we make our single bonds coming off the central atom. Each of these single bonds is 2 electrons. So that is 2, 4, 6, 8 electrons we've already used in doing the first step. So 32 minus 8 is 24. So just to recall. So added the valence electrons, adjusted for the charge, determine the central atom, connect all other atoms to the central atom using single bonds. So that's the step we're up to now. So of the 32 total electrons, we just used 8 for the single bonds. That leaves us with 24 left. Now the next step is complete the octets of terminal atoms first. So oxygen is our terminal atom. We're going to need to add all 6 of the electrons oxygen needs to have an octet. An octet means 8. There's 2 that it's sharing with this phosphorus, and then the other 6 are coming from the completed octet. So we're going to complete that for all the oxygens. Now each oxygen has 8 total electrons surrounding it. That required us to use the remaining 24 electrons left. So 24 is what we had left. We used all 24 to surround the oxygens. We now have none left. But look, phosphorus has a complete octet, 2, 4, 6, 8, and each oxygen has a complete octet, 2, 4, 6, 8, 2, 4, 6, 8. 2, 4, 6, 8, and 2, 4, 6, 8. So we're all good. So PO4 looks something like this, and we'll talk about that some more in a minute. Let's do one more. So nitrate, NO3 minus 1. I know you all like it when I keep the minuses there. Nitrogen has 5 valence electrons, oxygen 6 valence electrons. There are 3 oxygens here, so we need to multiply that by 3, so that's a total of 18. And then, since we have a -1 charge, we need to add 1 more electron for the -1 charge. 18 plus 5 plus 1 is a total of 24 electrons. Our central atom is the first one listed, unless hydrogen. That is not hydrogen, that's a nitrogen, so we're going to put that in the middle. We are going to bond all the outer external electron atoms with bonds. And remember, each bond is 2 electrons, so there's 2 there, 2 there, and 2 there. So of our 24 electrons available to us, we've just used 2, 4, 6. We just used 6 for the bonds. 24 minus 6 is 18. Now we do the next step, which is add valence electrons to the terminal atoms, the ones on the outside. So that's 1, 2, 3, 4, 5, 6 needed for oxygen to have a total of 8. With these 2 here, oxygen needs 1, 2, 3, 4, 5, 6. For a total of 8. And then with these 2 electrons here, oxygen needs another 1, 2, 3, 4, 5, 6 for a total of 8. So we've used now 6 plus 6 plus 6, 18 electrons to do our terminal octets. We're down to 0. Now we're finally going to use this other rule. Complete the octets, place any leftover electrons on the central atom. We don't have any. If the central atom does not have a complete octet, which is where we are now, form multiple bonds. So our nitrogen has only 2, 4, 6 electrons around it. It needs some more. So we're going to need to double bond with one of these oxygens. In a double bond, each bond takes 2 electrons. So one of these oxygens, in this case, I pointed out to these electrons are going to come here and form a bond. And that's what happened here. So we have a double bond here, single bond, single bond. So this is one way of describing the nitrate anion, where there's a double bond here. But if you'll notice, there's really no difference between any of these oxygens, right? I could have chosen this one. I could have chosen this one. And this is a fine representation for what's going on. I'll give you credit. Don't sweat it. If that's the last you want to hear of it, stop listening now. But for those of you wondering, hey, how did you know to use that one, not this oxygen or not this oxygen? Let me just number them like 1, 2, and 3, right? How did you know to use 1 and not 2 or 3? And the reality is there is no difference. And each of these would contribute about 1/3 of a bond. So each of these, if you look at the bond length, if you look in a microscope that can see the nucleus of these atoms, you would see that the oxygen and nitrogen of all 3 of these are the same distance. So what that means is basically each of these bonds is basically 1 1/3, and we call that a resonance structure. That is a little higher level. If none of that made sense to you, don't worry about it. The point is you're going to double bond one of them and move on. All right, so ozone, O3. This is an important molecule, we have oxygen, has 6 valence electrons. There are 3 of them. So 6 valence electrons times 3 is a total of 18 valence electrons for this molecule. Now, it doesn't matter what we choose as a central atom because there's 3 of them. So we can choose an oxygen. 1 oxygen, 2 bonds, 1 to each of the terminal oxygens. So that's a total of 4 electrons. So we take 4 from 18, we got 14 electrons left. We're going to need to complete the octet for the outer atoms. So that's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 plus 6 is 12. So 14 minus 12 gives us 2 left over, and the 2 left over are going to go on that central atom, 1, 2. So now while this has an octet, there's 2 in the bond, 3, 4, 5, 6, 7, 8. This has an octet, there's 2 in the bond, 3, 4, 5, 6, 7, 8. This central one's getting a little hosed here. It's got 2 here, and just 2 there. So it needs 2 more electrons for an octet. So we're going to, again, have to double bond, and we can choose either one of these. We can choose this one to give the double bond, and that'll give you what's shown here, or we could have chosen that one to give the double bond, and that'll show you what's here. I show you this plus minus. That's not as important for what we're doing, but because, anyway, I'm not going to get into that. But that's true. Basically, there'd be a plus minus, but notice an overall neutral charge, so there is no charge to the whole thing. If you really want to talk about that, come see me, and I will talk to you about that. All right, and then we get into VSEPR, and I'm going to hold off there. I will make that a second video since none of you are going to want to listen to me anymore. So thank you very much. Hope that helps. I'll talk to you later.